Hi, good afternoon everyone. Welcome to day 2 at the Supercomputing Asia 2022 conference. This is the industry track. I'm Dr. Irne Zidar and I'll be chairing this session. First, just a few rules. If you want to listen to what the speakers are talking, please use the silent conference system and tune it to channel number 5 as indicated there on that board. Also, please do not hesitate to drop any questions that you may have for the speakers. At this conference, we're using the Pigeonhole system. The web address is www.pigeonhole.net, and just use the password SCA22 and just submit questions for it. Now, without further ado, let me introduce our first speaker, Dr. Karthik Sundarraj, Technology Advisor at Hexagon. And the title of his presentation is Next Generation CFD for Real-World Applications. Mr. Sundarraj, the floor is yours. Thank you.
Thank you so much. I first of all want to thank SCA 2022 for giving this opportunity. I also want to thank NSCC, and I hope today's presentation will give some insight towards how CFD can be used for real-world applications. I think most of us are aware of CFD being used in very specific and focused industries, but today I really want to throw some light on what I mean by real-world application and how is CFD really, helping the nation build different industry segments. So I don't want to introduce too much of CFD. I'm sure the crowd today is already aware, but just a quick understanding of what we know about CFD. So CFD is a very digital representation of all the fundamental physics that involve flow, heat transfer, and mass transfer. So it is safe to say that pretty much every fluid, every particle, every semi-solid and every semi-fluid, which has the characteristic of a flow, can be simulated using CFD techniques. I think typically CFD gives you outputs like flow fields, the forces, pressures, heat transfer, mixing rates, and many, many other things. So, like I said, CFD is pretty much used in every industry. It almost touches all the industries that we are aware of, starting from the typical applications in aerospace to even a very unique and specific application when it comes to food and beverage. I think CFD touches all these particular industry segments. Now, there are certain reasons why CFD is used in these industries, and some of the reasons, that is the benefit that people get. For example, I'm taking the example of AnalogWay. Now, they use CFD on a day-to-day basis to save their design and development time. Okay, so their entire video and audio systems are expensive and they develop these unique products for unique customers. So for them, time is very critical, and CFD helps them achieve this using the unique CFD methods. Then we have the example of Panasonic, where Panasonic uses CFD regularly for reducing cost. Okay, so they use typically CFD for safety validations, they use CFD for performance, they use it for re-engineering and product improvement. Then we have another very unique example of North Face. Now, very few people may know that a company like North Face can also use CFD. And they use CFD for their jackets, for their winter clothing. And this is typically to boost their innovation in sportswear application, particularly in cold environment. So they are trying to use CFD to understand flow movements and thermal regulations that happens inside a jacket, and also considering the outside temperature effects. And finally, we have universities, we have institutions We have organizations such as these where they use CFD for future technologies. So these can be sustainable technologies where solar power is being harvested, wind power is being harvested, or these could be technologies like EV, which is the future of the globe, or ADAS, or maybe aerospace, hypersonics, many other things. So CFD again plays a very, very important role in these type of sustainability and future technology initiatives. So let us see that while we talk so much about CFD, definitely CFD has its own challenges. And these are some of the typical challenges for an engineer who does CFD. And these are endless dreams also. I mean, it's right to say that since the time I've been using CFD, that can be close to 15 years, these challenges have been constant. It's not that they have improved. So one of the typical constant is workload. That is the pre-processing time an engineer spends in doing CFD. That is, it may be CAD cleanup, it can be simulation time, or it can be the accuracy, the amount of time put towards generating an accurate, stable CFD solution. The other is fidelity. Okay, that is how accurately are you able to predict? So, for example, for CFD users, if they use a RANS method of simulation, they know that it is going to be quick. But sometimes the problem may require an LES approach, which is a much more advanced method of simulating and analyzing CFD. But of course, this has the price of fidelity. It has the price of time. It has the price of infrastructure. So that becomes another critical challenge. And lastly, now that CFD is being applied for large models, okay, where people have started using CFD for large area simulations. Of course, with increase in size, the mesh count increases, so the computation time increases, your requirement for or the need for IT infrastructure also increases. Now, with all these challenges, we are also talking about productivity of an engineer, of a person who is doing CFD. So CFD groups are constantly requested to increase their productivity. That is how they can reduce the time they spend on CFD. Can there be incremental increase in time saved while performing a CFD activity? And this becomes a huge challenge for an engineer, because at the end of the day, the engineers only have 8 hours of time. They have to run cases overnight, and it becomes difficult for managing time, particularly with cases like CFD, which is large scale in nature. Like we have scenarios where we have been running cases for over a month, and still there is no convergence achieved. There is no accuracy achieved. There may be errors. So you may be running a CFD case for 20 days, and on the 21st day, the CFD may crash, and we are completely lost that entire 20 days or so. So CFD again is a very, very time intensive simulation approach, and productivity really means a lot here. And always there is a tug of war in CFD, whether to go with accuracy, whether to go with speed. I would say we always try to be the middle, but this tug of war is going to remain for many, many years to come. So what we do is we first address the pre-processing aspect, okay? Large models, thousands of parts. How do we achieve that 10x productivity? So can we incrementally improve the time that an engineer is spending on these type of large models, these type of models which has thousands of parts? So typically the time spent is on CAD cleanup, you do a wraparound mesh and many other activities to perform a typical meshing. Now, we have this, pre-processing issues of identifying holes and many CAD related issues. But what happens is an engineer typically spends close to 20 hours for a typical scenario of a simple engineering outcome. We have these newer meshing techniques called voxel fitted meshing, the wraparound meshing, where the entire CAD cleanup phase can be eliminated, and your time you spend on pre-processing drastically drops down from what it used to be 20 hours to what it is 2 hours. So Cradle CFD is also capable of doing these type of voxel fitted meshing through which you are able to achieve the 10x productivity. Okay, the other important area is scalability. Okay, so what you see here today in this video is basically the Olympic Games in Tokyo. Okay, we have simulated solar radiation, heat island of the stadium, wind simulation. We also made special focus as well as on the human thermoregulation model. So what you see there are thermoregulated athletes where we are trying to simulate their healthcare issues like atmospheric temperature, humidity, and so on. So if you remember, in 1964, the Olympic Games were postponed to October, primarily because of the heat stroke issues that the athletes were facing. Okay, so we took this scenario to create a very large scale simulation model and perform this entire simulation activity on a Fugaku system. So if you see here, for this specific simulation, we have run it with 216,000 cores on the supercomputing platform Fugaku. And we also believe that we broke the world record of CFD commercial code parallelization. So this is one of its kind example, what you see. So it's a combination of heat island effect. It's a combination of thermoregulation. It's a combination of wind simulating around the stadium, as well as the solar radiation. Now, the advent is, of course, like I said, we are working on a simulation which is extremely time consuming. So we now want to do real-time CFD by performing digital twin models. So here is an example of a reduced order modeling of a simple restaurant HVAC system. We use AI ML tool to create digital twin of this and perform DOE-based simulation, design of engineering-based simulation. So what it becomes is quite easy to optimize and play with input parameters to determine where are the best locations for HVAC inlets and outlets, and what one CFD calculation might take about 30 to 40 minutes to perform this simulation. By doing this digital twin approach, we are really able to do the same simulation 80 times faster. That is, what was taking 30 to 40 minutes can now be simulated in 30 seconds. So this is where reduced order model, AI ML approach really impacts the approach towards CFD simulation for the future. So the next thing is, of course, we achieved 10x productivity. Now the importance is of achieving 100x productivity. That is one of the reasons why I showed the previous two slides on scalability, where we are able to scale the software, CFD softwares now to 2,200 plus cores, 200,000 cores, and so on. The other important thing is availability of infrastructure. Now, for people who do not have infrastructure, that is when AI ML comes to their support. So with a combination of scalability, with a combination of AI ML, I am 100% sure that we can achieve 100x productivity in CFD itself. So what used to take 10 hours will now take 1 second. What used to take 100 hours may now take just about a minute or so. So that is the sort of productivity we are seeing with the AI ML integration into CFD. So at this time, I want to take you through one example of how the solar farming digital twin works. Okay, so this is Hexagon's solar farm in Archinoda. What we have done is we have done scanning, we have used geospatial systems, and we are using CFD modeling to create a digital twin of this entire solar farm. Okay, so if you notice, we are performing the geospatial activity using some of these softwares. We are creating digital twin by performing laser scanning, and then we use these type of 3D models to perform the CFD. Now, how are we doing this CFD? So you can see here, these are the CFD models for different parameters. Now, what you notice is that we are integrating this with AI ML over here. So a typical CFD run for us took about 2 hours. And now with AI ML integrated, it takes about 2 seconds. Okay, that is where technology is. So CFD integrated with AI ML can give you host of opportunities to try different parameters. And a very interesting application is the usage of AR VR. Okay, so visualization is critical. CFD visualization is of very critical importance because people need to understand these technologies, and AI ML VR gives them a very closer understanding to what we are demonstrating. So what you see here is you can visualize CFD through headsets. You can visualize CFD through a simple iPad. So these are all virtual reality, artificial realities, integrated with CFD, integrated with AI ML. So we are talking about a highly advanced approach towards performing CFD simulation for such large area applications. Another large area application is wind farm placement. So what you see here is we have weather data, we have GIS data, and the uniqueness is we can combine weather data, we can combine GIS data into this single platform. Basically, this approach is very important to locations for wind farm locations. So you typically understand the wind flow generation, the terrain mapping. How do terrains really impact the performance of these wind flows and so on? And you can go one level up to also integrate wind energy simulation because of a collaborated wind farm. The next approach is to understand effects of placing these wind farms. So you know that wind turbines generate a lot of turbulence. Now, placing multiple wind turbines one behind the other may have a lot of wake issues. So what you notice here is this particular placement itself has multiple probabilities. So the placement distance can change, the placement locations can change, wind directions can change. So there are a lot of variables and there is opportunity to do a lot of CFD. But because this is large area simulation, definitely a CFD approach will take huge amount of time. So that is where we again use a AI ML approach and then predict the CFD simulations coming out of it. The other very important large scale simulation is disaster. Okay, so how do we manage disasters? This is a very good example of flooding and breakage of dam. Now, this project is extremely complex because it uses close to 4 kilometer by 4 kilometer area. The terrain is taken from drone and the terrain is taken inside CFD. Then there is water flowing. Now this water is flowing for multiple kilometers. Okay. And this is a VOF approach. So for those of you who are CFD experts, you may be aware that a VOF simulation is quite complex. And then finally, you see that we are also building a dam over here and then performing a dam breakage situation. So if a dam breaks, what sort of damage and disaster will it create during that situation? So a very complex scenario and definitely requires good amount of IT infrastructure. And these type of simulations are essential for a city, for a country who are really looking forward to manage disaster in a smart way. And so it is highly important that these type of simulation methods are implemented, but also since they are time consuming, we need to see easier ways of performing these activities. And the very good recent event is COVID. I think COVID really gave insight towards using CFD in a very different manner, mitigating infection transmission, right? So One is containments. I think during COVID, a lot of containment activity happened. So this is an example of a portable ICU where we are using HEPA filters, activated particles, cleaning of people who are entering ICUs and so on. Infection prevention booths, that is a doctor and a patient trying to meet. How can you use effective filtration methods to keep the viruses contained while this discussion is happening, and many other things. I think even ASHRAE has given a clear mandate on how the ventilation should happen to avoid recirculations inside operation theaters and so on. And one of the other thing is distancing effectiveness or the droplet dynamics. Every country started telling what should be the distance between two people. Now, how do we know that these are effective distances? And people started saying that you need to wear masks to control the disease. How do we know which mask is effective? How much of particle is it able to contain? And how much of particle can it not? What should be the size of particle and many other things? So CFD gave that insight on mask usage, distancing effectiveness, closing and protecting yourself while speaking, being in public areas, and many other things. Now, there are a few countries who also took to large area disinfection. And there again, CFD played a very good role in understanding what is the time that you need to do disinfection, what is the area that gets covered while you perform these type of disinfection activities. Then comes the advancement in technology, that is 5G communication. Now, in these type of applications, multiphysics plays a very critical role. So what you see here is an example of how you can use CFD to typically recreate a failure mechanism. Now, electronic component fails for various reasons. It can be humidity, it can be rain, it can be dust, it can be solar radiations, it can be thermomechanical stresses, or it can be vibroacoustic and noise. Now, with the help of CFD, with the help of multiphysics, with the help of co-simulation, you are able to create a complete scenario of events in which for example, in this case, a 5G equipment can fail. Now, also touching about e-mobility, I think e-mobility revolution is highly dependent on CFD. That is my personal opinion. I'm just going to share a few very critical examples. For example, a motor. So electric vehicles range anxiety is always dependent on the energy required for IPM motors. Reducing the size, minimizing the weight, and keeping optimal operation temperature is what is going to make it an effective thermal management scenario. And that has a role of CFD to play heavily. Now comes the battery modules. I think thermal runaway scenarios, safety issues of batteries being used. For example, in this case, even if one cell overheats, the meltdown will spread and it will continue until the entire pack is destroyed. So what you see here is just one cell getting overheated, but the entire battery pack gets destroyed because of that particular activity. So early detection of thermal runaways is very critical and very important. Again, CFD plays a very important role here. Whether it is power electronics, whether it is effectively placing a sensor or a camera, because future mobility, that is ADAS, electric vehicle, are going to be heavily dependent on power electronics, heavily dependent on sensors and cameras. So here again, CFD plays a very, very important role. Then advancements in aerospace and defense. So what I'm trying to do today is telling you what are the future areas in which CFD can really contribute. So one of the most important area which aerospace and defense is venturing into is re-entry or going to different planetary systems. For that, we are talking about aerothermal heating. Okay, so maneuverability becomes a very critical aspect. I'm just showing you some examples of how hypersonic, transonic applications, defense areas, co-simulation really work. And one of the important areas is drone. Okay, so we have moved away from fixed wing drones. We have moved away from quadcopters. Now we are talking about advancement in drones, that is flapping wing drones, micro drones, who are capable of doing multifunctional activity and not just flying. And finally, I come to the last part, that how CFD can really make an impact when it comes to smart buildings, HVAC. Okay, so you are all aware that buildings can be scanned. So I'm just showing you a roadmap of what I mean by smart buildings. So we take old data set, convert it into 3D point cloud data. Then the BIM data set comes into picture, where the cloud data is converted into 3D CAD, and then the CFD simulation, usage of AI ML, and finally using these simulations in an augmented reality. Okay, so what you see here is an augmented reality approach towards visualizing HVAC, visualizing building simulation, effective airflow movement, so on. So this can be the outcome of a CFD. So no more CFD is colorful fluid dynamics. Now CFD is very, very meaningful fluid dynamics. It is very essential for your day-to-day simulations. Lastly, what I want to show you is, while we talk about all these things, we were speaking about smart building, we were speaking about EV, future mobility, but smart cities, that is the future. Okay, new districts have to be fully renovated or built by integrating wind simulation for pedestrians, green areas, shadow effects when summers are hot, etc. So this is a small example of Munich city, where a wind simulation was superimposed to the scanned city data, and you can do these level of simulations with the help of CFD. So with that, I thank everybody. Thanks for the opportunity given. I hope this presentation could give you some insight towards what is there as an opportunity for CFD. And we as a company, Hexagon, we are into these particular technologies, and we look forward to collaborate with whoever is interested in this forum. Thank you so much. Thanks SCA, thanks NSCC. Thank you a lot.
Thank you, Dr. Sundarraj, for a very insightful talk. I'm really happy that AI and ML is moving into the CFD field as well, and you really presented a number of tangible benefits. Our next speaker is Mr. Sandeep Lodha, CEO and Director of Netweb Private Limited, and the title of his talk is Managing HPC with Mixed Workload Infrastructure. Mr. Lodha, the floor is yours.
Thank you, Dr. Genraj. I'm Sandeep here from Netweb Technologies, and basically I'm a director and also the CEO of Netweb PT Limited. So today I am going to present you about our mixed workload and the concept which is arriving for the modern way of looking at HPC and other workloads which are getting mixed up. So before that, I will give you a brief about our company. Today we do have presence in about 5 countries. We do have more than 7,000 customers worldwide. We do have more than 500 HPC installations. We have been doing a huge amount of GPU and other accelerator-based installations. We do a huge amount of cloud deployments, and we have been doing in multiple countries and managing those cloud. We also have a team for designing big data setups, right from ingesting to final analytics and AI. And we have been also giving turnkey solutions for AI and other stuff. And yeah, so we do have 3 integration facilities and things like that. So just to give you an idea on our products and solutions. So of course, for the data center computing, we do have more than 500 server variants with us. So what we essentially do is, we say that whatever the requirement is there, according to that, we can customize the hardware thing. And we do have a huge number of choice to work on that. We also have a whole range of storage product. We do have unified storage products where we do have SAN, NAS, and VTL in one box. and this can connect to any kind of a network, starting from all kind of gigabit Ethernet to fiber channel and also InfiniBand. We do also design a lot of storages for cloud, specifically Ceph and Sinter-based solutions also. We do, in fact, a lot of PFS designs for our customers, and we are also getting into specialized container storage solutions for containers, which requires quite a different way of looking at things and how those can work. On the HPC side, virtually we are into everything, and we do have also a management tool which helps out in, and I'll be speaking more about that a little later. Talking about on the cloud side, we have been doing a huge amount of cloud. We have been working with a lot of telecom customers today, and we are deploying world over the telecom clouds, specifically for the 5G requirements, what is going on. We are also having a lot of cloud tools and things like that. I've already spoken about our big data offering. And on containers, I would be speaking about that we do offer a new platform for containers. And I would be speaking to you more in details as I move ahead. So these are our engineered product solutions, which I would be targeting today also in my mixed workload concept. We do have a container platform. This is an upstream Kubernetes platform. We also have a Cubites, which is a container optimized cloud, basically HPC and AI cloud ready, containers ready on the cloud. Another product is Skyler, which is a very easy way to hyper-converge infrastructure on cloud. And the last one here is TCM, which is Tyrant Cluster Manager. And this is basically for your deployment of HPC. So let me come to my main topic today. So what is happening is today, we would have already seen that HPC and AI is getting a lot converged now. And then what we are also seeing is that there are many workloads which are coming up, and new way of doing things are happening. So we define this mixed workload as FORCE. This is an acronym which we have devised for this. So basically, we all want a very flexible, flexible infrastructure. So how flexible it can be, how we can define those flexibility. And today, there are a lot of workloads which are coming up. How do you optimize them? The another issue is that we need to address those optimization things which we need to work on. We also require a lot of resilience now, and to see that the applications are running at all the times, and we do have the failovers and things like that. We need to configure them, because there might be a diverse requirement which is more prominent at that particular time, and we should take less amount of time to do any of these kind of things. And of course, the ease. We must be able to do all these things with the most ease possible. So this is the architecture we have been using for a lot of our customers, and we are quite successful in this. So if you see, there is a GPU workload which is there. I mean, it can be a bare metal GPU. You can have a bare metal HPC. I've got no issues with that. We can integrate with this particular solution. And then what we can do is, this is an entire cloud setup which is there. So somebody can do is, they can come to a VDI on a virtualized environment, and we can give a VDI solution. So the authentication issues, whatever is there, is tackled when you are is tackled when you arrive to the VDI setup on the cloud. And from there, you can access any part of things. You can access the bare metal GPU, bare metal HPC, or any part of the thing. And inside this, you can have a composable big data cluster, a very easily set up big data cluster, or a virtualized HPC, or you can run HPC or AI workload on containers. And you can also trigger all your orchestration from here to any of your bare metal infrastructure also if you want to. So you can do it in various configurations. It is not necessary that you need to do in one configuration. And you can also have a hybrid approach here and can connect to a public cloud. So basically, you can start looking at your infrastructure in a different way and try to give it more flexibility. And slowly, you will be able to define, as the modern workloads and the things are going on, you will be able to define it more better. And it is so flexible that you can keep on changing it as you want. right? So the thing is that, why we need a container, I mean, I'm talking about another part is that why containers are required in HPC today. So if you see, today, we need optimal utilization of the resources. So the resources, if the resources are optimally utilized, you might be running a load, but there might be still some scope to utilize those resources. So how we are going to optimally utilize those resources, and containers are really going to be handy for doing all those kind of things. Then again, another advantage is going to be running heterogeneous workload at the same infrastructure. So you might be maybe you're running a same application, but there can be a different version of that application. You want to run on the same infrastructure. And so how do you do that? Containers are going to help you with those. Another big advantage is going to be the portability. Taking the application, which is you can port from bare metal to a OpenStack cloud or a hybrid or to the public. So you need not change anything. You just have that container which is going to be ported everywhere. So containers are really going to be very, very useful for that. It is going to be easy to maintain and upgrade. So anything is there, and you can keep on various versions for yourself. You can have your own repository and those kind of things. So another big advantage is you can scale on demand, and it is going to be very quick to deploy. You need the application to run. You are ready with your data. You just start the container, and the setup time is virtually not there. And imagine if you are on public cloud, any application which can be containerized, you won't need any setup time for that. So you are going to be very, very fast on the HPC, right? And we are also getting bare metal performances, almost a bare metal performances on container. And this is going to be one of the big things where we see that containers are going to come in HPC arena. And it is also compatible with traditional schedulers today. So what happens is, if we have to match up with the original setup and where we want to use them, and you want to use some of the traditional schedulers, so we can also make it compatible with that. Right. So another thing which we are doing is Cubites is a container repository basically, and we do have right now ready repository of more than 100 of containers for more than 50 applications. You can run the application from anywhere on Cubites without any trouble. You can run it on the bare metal, you can run it on the cloud or on the workstation and things like that. And it makes your deployments very easy and very fast. So currently, to give you some idea on some of the containers which are ready right now. So these are the containers which are there, and we do support all kind of containers. We do have a CPU optimized containers, we do have a GPU optimized containers, we do have AI optimized containers. We are also going to bring in this repository many other containers which are specific to certain organizations, but we'll try to optimize most of those and try to put into the repository. So you will have ready-made huge amount of containers, and suppose you are okay with you are testing out certain containers and you feel that this is good, so you can take out those containers and keep it in your personal repository, and you can allow your users and other people to use them more often. So just to give you an idea, we ran the same code on LAMPS, NAMD, and GROMAX on a bare metal and on a Cubite container. So if you see, the performances are mostly bare metal performances which we are getting. So this is, and we are optimizing more and more applications now. And I'm sure that, that there are two large concerns always there with the containers, which was there, the security. And another was that, can it scale from more than one machine? And these both are possible now. And we are getting good performances with those kind of setup. So the idea is that if we can work on something like this, it would be great. So the idea is, right now we are shipping out Cubites with our workstations. So most of our workstations do have Cubites, but we are coming with the various models to deliver Cubites. And it will be available in a lot of flavors to most of our people so that they can use this. It is available for both CPU and the GPU optimized. It is available for both AI and HPC, and we are going to have many more types of containers to be there. Yeah, and we do have a team of experts. Suppose somebody, if you have got any kind of a container, if you want to get it converted to optimize for the on the Cubites, we are ready to do that services also for you. So this is an example of a workstation which I was talking about. So basically what happens is the installation times, the download time is in seconds, and you are up and running and with the performances which are good. So you can run multiple applications also simultaneously into your workstation. And slowly we are bringing this to your clusters and cloud and all those kind of things. Right. So I was talking about our Skyler's product line. So this is a very easy to use cloud solution where we do have ready templates for your big data, HPC, also container packages and all those kind of stuff. So basically you can start using this, and this is also having a multi-tenancy. So suppose in a department you want to give set up some resources for a particular department, and you keep them free to do whatever way they want to run it. So they can easily do it on this cloud. So very easy to set up, and it is optimized for typically for HPC and AI workload. We have put in some secret sources also there. Right. This is probably my last slide. I have got some time maybe for some question answers. This is our TCM. This is Tyrant Cluster Manager basically, and this is for your deployment, redeployment, provisioning of your hardware, and managing your entire infrastructure. So this is our package for this particular thing. And I don't know how I would be getting the questions, but I would be glad if I can get some of those questions. Or somebody has got any questions?
Right. So there are no questions in the pigeonhole, but I really like your solution because it really promises, especially the container bit. I have a passion for containers, and I really appreciate the effort that you put in, because it is a major issue when one goes from on-premise to the cloud.
Right.
How you handle the software stack, and as you mentioned, containers are literally the way to go, and it's really good to see that they are the HPC community is embracing them. So thank you for a very, very interesting talk, and I wish you all the best.
Thank you so much. So we are working with along with a lot of schedulers and also working in Kubernetes, and we might also have certain orchestrators also bundled up, so that it is so easy for you to keep on moving.
Oh, okay, that's really good.
Yeah, so we'll try to do all those kind of things also. So we have got a big plans on Cubites. Yeah.
Awesome.
Thank you so much.
Great.
Sir.
Thank you so much, sir. So our next speaker is Dr. Xavier Vigouroux, and the title of his talk is Atos Life Sciences Center of Excellence, Boosting Innovation. Dr. Vigouroux?
Can remove the mask. What a relief. What a relief. Okay, thank you first. So yesterday, during her keynote, Agnès Boudot presented our new supercomputer XH3000. In fact, this is our latest supercomputer that we will deliver, and Atos is delivering supercomputer for more than 15 years now all over the world, and this XH3000 is the latest one. So obviously, this supercomputer, as a lot of supercomputer, is very versatile. We can do many, many things with that. So the question is how we can deliver value to a specific domain. So today, I will present here the Atos Life Science Center of Excellence, and the goal is to bridge the gap between the technology and the use case. So starting from the technology we are providing and going up to the use case. So my name, as I mentioned, is Xavier Vigouroux, and I'm coordinating the strategic collaborations in HPC AI and Quantum division, and I'm also co-leading the HPC AI Quantum Life Science Center of Excellence. And in fact, I'm not alone in this Center of Excellence. We are two. I am more on the technological side, and we have Natalia Jimenez, who is bringing his knowledge in the domain with a clear background in life science, with a PhD in life science, with a lot of energy, and she's also a distinguished expert member of scientific community, so trying to take pieces everywhere just to be sure that the Life Science Center of Excellence is targeting the right thing. So to demonstrate this, our will to go to this domain, we have decided to set up a physical center of excellence with a some kind of virtual and hybrid event. It's very good to have a physical space in which we can share ideas and bring demonstration. So, So this center of excellence, in fact, is based in the Wellcome Genome campus close to Cambridge, in the south of Cambridge, and this place is where the Human Genome Project took place in 2003. So it's a very long track record in the genome, and they have decided to have some spaces in which we can demonstrate things. And the Life Science Center of Excellence is based in this domain and will be launched because of the COVID. It's not physically open, but the activities have already started. It will be launched in the coming weeks. So the goal of this center is, as I mentioned, to bridge the gap between the Atos technology and the life science use case. So we have the two sides. There are many technological options, and there are many domains in which we can apply things. So first, let's see how Atos is building his vision. So the vision is not only focused on the HPC. So the HPC is obviously the cornerstone with a lot of computing power, but HPC cannot solve every domain, every problems. There are some problems that cannot be solved numerically, and these are, for instance, the ones solved by AI. Yann Lequin is used to mention that he doesn't know how to write a program recognizing a cat in an image. AI and data-driven approach can provide this info, can solve this problem. HPC cannot. And the last step is the quantum approach that will solve, or the promise is that it will solve currently problems that are untractable with the first two. So today we have a mature solution, HPC. We have the AI, which is becoming pervasive in every domain, and we have the quantum. And in the domain, I will switch to another thing first. This is the first vision. Second, we have the digital challenges on the life science side. So we consider we have these 5 big challenges we want to solve with improving drugs development, maximize the data, the value of data, enable precision medicine, obviously, and then enabling digital industry ecosystem and digital hospital. So here I'm focusing on the first one, considering that with our technology, we can improve the drug development, we can maximize the value of the data, and we can enable the precision medicine, and I will prove why we will be able to do that. So let's see first some use cases. So the first one is the protein folding. Everybody knows this issue. When you have some amino acids, a long chain of amino acids, and you want to see how it will fold in a structure, in 3D structure, and how you can compute this 3D structure. Today, we are solving that with some HPC solutions. And it works fine. It works fine. Now, in 2019 and 2020, DeepMind, with the AlphaFold program, has been able to solve this problem much more efficiently than ever. So this is the best core. There is a challenge that takes place every year. And instead of having a numerical solution, in fact, DeepMind with AlphaFold proposed an AI approach solution. In fact, this solution is considering the distance between each amino acid and try to learn what is the distance between amino acid when I present a sequence. So we can see here that we have a HPC solution, and then we have a better solution, which is the AI. And last step is the quantum. The quantum, if you look at the number of configuration that we could have with 100 amino acid, is 10 to the power 47. So obviously, we cannot enumerate anything, and we will have to have some heuristics. And then for optimization problems, for sure, quantum is the right way. So this is an example here, but we just have a folding of a protein. So how we can move forward? So the idea is to say, okay, considering the folding, let's look at the very well-known COVID-19 today. And in fact, there is two configurations in terms of folding. There is an open version, an open one, and a closed one. And we have to, the one is active. So sorry for that, I always miss between the open and the closed. But when it's open, the spike is active, and when it's closed, then it's not active. And the question is when we will be in a situation and when we will not be in a situation, and also how we can dock something to avoid this site to be active. So here, starting from the folding, we can solve this issue and understand how the spike is active and not active. And there is a next step. The next step is to start from variant. So we have a chain of amino acid. We look at the different variants, and then we consider the 3D structure of this protein. So we have a proof of concept currently running with University College London and with ARM, where we'll start from the problem of the variant detection, and we go up, we went down to the workflow, to the 3D structure of the protein that's been raised. And the goal is obviously, once we have this 3D structure, to see how we can put dock some kind of ligand into this protein, and we can see if it fits in a pocket. And so we can have precision medicine and consider that, considering the variant that you have, considering a given ligand or compound, how we can fit in the pocket and solve your disease, not solve a disease, but solve your disease for your variant. And this is what we are trying to do right now with ARM. If we go further, we can consider, please, yes, we can go further in terms of, I would say, business, on the business side, is with the CENAG, which is a center in Spain. So here we are in the production side. CENAG is simply sequencing 800 gigabases a day, and they have to go through that and do all the process to have the full-scale DNA and everything in the workflow, down the workflow with all the identification. So here we have delivered a supercomputer that will run this number of bases a day. So again, from the research to the production, here we have a clear innovation, and they can run their workflow on the supercomputer. If I go even further, I will go even further in the next slide, sorry. We have a center of excellence in France, in Europe. There is a center of excellence called Combiomed. Combiomed is putting a set of applications, life science applications, in the same space, trying to deliver that to a community, to the life science community. So we are part of this center of excellence. Sorry, the name Center of Excellence is everywhere, sorry for that. But this one, let's call that Combiomed. Combiomed is trying to tackle 3 domains: cardiovascular, neuromusculoskeletal, and then molecular-based medicine. So again, HPC here is able to deliver a specific answer to different problems. The one we can go here to prove the power of the Center of Excellence is the cardiovascular one. We are able to simulate the full blood system of a human, and then considering the pressure and the speed of the blood in everybody, every arteries, everything. So we have one program doing that with a Lattice-Boltzmann for people who wants to have the details. This is a Lattice-Boltzmann resolution of the problem. And then behind, we have another program looking at the way heart is putting the pressure, and the electrical signal is going into the heart. And we have here, side by side, a set of tools that we can really dedicate to one person. Again, precision medicine is not here. We are not at the production level, but we are able to have the full body, my full body, and see if I have some issue with some places in the legs or things like that. The second thing, and this is the one I wanted to go through first in terms of business, again, our Center of Excellence this time is funding a PhD in a business school, the business school in Amsterdam, and they are looking. The PhD student is looking at two problems. The first one is for the diagnostic, cancer diagnosis. Sorry, with AI, computer vision AI solution to detect the cells, the sane cells and the cancer one. And the other one is interesting also, is the one concerning osteoporosis. This one, the student is looking at how HPC will impact the diagnosis of the osteoporosis. Considering that if we can reduce the cost of this study and make it faster, instead of waiting 2 weeks, you have a result in 30 minutes, for instance, what will be the impact in terms of I would say mankind somehow, of resolution of osteoporosis? So again, if we look at it, we have very early stage and research and fundamental actions in our Life Science Center of Excellence. We are more business-centric action as this one, and we have also contributing to the community with CompBiomed. So this is for the use case. Now, obviously, if we look at the Center of Excellence as a bridge, this is a bridge between the use case and the technologies. So in terms of technology, I will go through the slides that has been presented by Agnes yesterday. So this, the XH3000, I will employ it. So this is a supercomputer, in fact, that goes from the petascale to the exascale. So we can put just one rack or many of them. This is a very versatile one. So we can put in this supercomputer CPU, GPU, QPU, IPU, and we can make a really dedicated solution for a specific problem. If I look back to the POC that we have with ARM, we have the first phase, which is integer-based, integers and memory greedy, and the second phase, which is more focusing on floating points and more, that would be more efficient than GPU. Here, you can mix the both, and having a workflow with really specific nodes for a part of the workflow, and some other part that will be on another part of hardware for another part of the workflow. Carbon footprint, this is, just to mention that this is our fourth version of direct liquid cooling. So if you listen to carbon footprint and energy efficiency, you have heard about the PUE, the fact that when you put energy in this rack, what is the energy going through the CPU and not for the cooling? So here, there is only 1%, I would say 2% of the energy that will go to the cooling. It's only for pump. And inside, you can put hot water up to more than 40 degrees. So water that you have here, you can put it in this rack and cool it down just with pumps and a passive exchanger on the roof or anywhere. So this is how we got something efficiency. No chillers, nothing like this. Direct liquid cooling. Again, the same view with on the XH3000 with the exascale. The density, obviously, we have, compared to the previous version, we are 6 times more dense. So if you look at those 5 racks that we have here, there would be less than the 6 racks like this would fit in one today. And then we have, again, the flexibility, which is key today. There is no one CPU fitting all the needs. There is no general purpose CPU. Today, there are many, many, many solutions for a given problem. So then, you will have to be sure you have the right hardware for the right problem or the right balance for a given set of problems. It's much harder now to design a supercomputer because you have to fit different needs, and you have to put CPU, GPU, QPU, IPU, everything inside to be sure you are the most efficient as possible. And this is really, the flexibility is key here in terms of compute and in terms of interconnect. Last point, is regarding quantum, because I mentioned quantum, and obviously there is no quantum computer today ready for the race. So this is why the position of Atos is to consider that we have to prepare it. We have to prepare this new era with the quantum computer. And as you know, there is a the current phase is what we call NISQ. So this is a noisy quantum computer. So today they are imperfect. But even if they are imperfect in terms of results we can get out of them, we can still make some computation on that, or we can simulate how a computation can take place on that quantum computer. So today there are many solutions with ion trap, with photons, with a lot of solutions for the quantum. We don't know what will be the winner, and maybe there will be several winners. So today, if you want to prepare this phase, you know that there will be several solutions, and you don't know what quantum computer will be the best for your own problem. So the idea of the QLM is first for you to be able to port your algorithm and to design the algorithm for the quantum world, and then to simulate how this quantum algorithm will run on a given architecture with a given technology, with a given topology, and having a result in terms of the quality of the results you will get. So today, if you are relying on this QLM, quantum learning machine, you will be ready once a quantum computer will be on the market. You will be ready to use that. You will be able to program that. You will be trained, because we can train that. You will be able to have exactly to determine the result you will get and the precision of the results you will get out of it. So today we are preparing this new approach and making our customer already using this machine ready for this phase. We have many customers. I will not go through that. In terms of impact, quantum computing is impacting every domain, from machine learning, from maths, computing, optimization, route planning, everything. This is for sure. And the biology, obviously, and you have the precision medicine inside. Every domain will be impacted. Obviously, there will be sub-part of this domain. So the quantum computer is not needed for every part. But this is clear that for health and life science, the quantum computer will change the game. Thank you again. Sorry, I think you would have preferred that Natalia would have presented that. Sorry for the gender balance, but I think she's larger than me. Look.
Thank you, Dr. Vigouroux.
I have to put it.
Yeah.
Okay.
I apologize for butchering your last name earlier.
No problem.
No, it's also my French is really bad at the moment. I want to thank you for a very good talk. I like that you presented how HPC can be used, especially in the case of COVID, to develop really targeted drugs for future strains. And I think we can all agree that we don't want this to happen, but it's really good that it does. Another point that you brought out, I feel was really good, that it's much more difficult to assemble or get a supercomputer now because of all the heterogeneity that one has to account for and all the use cases. So, and the third one that really impressed me was that you are already thinking ahead about quantum. And as you mentioned, there may be many winners in this race, and it's really good that Atos is looking forward to that.
Yeah,
so, thank you so much.
I'm coming, just a few words, I'm coming from the application side, in fact, with the benchmark. I was leading a benchmark team. And for me, the key decision is taken by the application result, how fast you get it, what is the result the precision of the result you will get. And again, starting from the problem, we must go up in upstream and to see what is the best solution between HPC, as you mentioned, with the flexibility, AI, and the quantum. I fully agree with you. Thank you. You got the point.
Thank you so much.
Thank you.
And moving on to the next speaker, we have Professor Pawel Gepner, Senior Hardware and Systems Field Application Engineer at GRAPHCORE. And the title of his talk is Convergence of Machine Learning and High-Performance Computing Systems for Empowering Classical HPC Workloads. Professor Gepner, the floor is yours.
Hello to everyone. My name is Pawel Gepner. I'm GRAPHCORE Senior System Engineer, and unfortunately, I'm not able to be in Singapore today, but I would like to welcome you to this pre-recorded session where I'm going to give the talk regarding convergence of the machine learning and high-performance technical computing system for empowering the classical HPC workload. Let me outline the agenda first. We'll start with a very short introduction about the GRAPHCORE. Then we will look on the IPO architecture details. Then we will discuss the pod system architecture. After this, we will look on the hybridization of the HPC and AI system. And finally, we will discuss our experience in acceleration of the scientific application and enabling them in the heterogeneity of the AI and the HPC solution. So very quick introduction. GRAPHCORE is UK-based company with the headquarters in Bristol. Our solution is based on the three fundamental pillars: hardware, software, and platform. GRAPHCORE developed processors specifically designed for the AI and machine learning workloads. We provide the hardware as the IPU processor, but also the software as the popular and the development tool as the complete solution to enable innovators and researchers to solve current and the future machine learning problem. Our platform utilized the current generation of the IPU delivered in the IPU M2000 fashion or IPU PodTrack scalable solution, which provides scalable deployment, small numbers that can be ramped up to tens of thousands of the system for the supercomputing scale-out. I will be talking more about it later in this talk. To better understand the motivation that guided our architects in creating GRAPHCORE IPU, we need to remember about the specific of the AI and the machine learning workloads. Today, computationally intensive programming runs on the dense data, applying no algorithm, producing precise answer. We know this very well from the HPC world. In machine learning world, we are dealing with completely new compute workloads based on the 6 fundamental principles. Massive parallelism. Tens of millions of the parameters need to be executed simultaneously. Sparsity in the data structure. Not all parameters connected to everything else, and the problems are very high dimensional. We need a mechanism which can go out and capture all those data together and gather it for the compute, and then scatter it back into the memory structure. Compute for the machine learning is in low precision. We are not using 64-bit calculation like we do in HPC. It is the group of all those small low precision operations that makes the high precision output. There can be a lot of reuse in the model parameter once they are loaded into memory for convolution or the recurrence, for example. Fundamentally, those compute graphs are static, like in the brain of human being. We don't rewire the neurons for every week or for every new task. And taking the advantage of the static nature, we can build the tools which can map our complex graph structure onto the complex processor architecture. Finally, entropy or noise. Machine learning models benefits from the injection noise. Dropout is one of the examples. So if we find a way to leverage those in our processor, we should be able to see efficiency and performance improvement. Let's have a look on the market and see what the type of the processors we have that are predominantly being used for the machine learning workloads. We have the CPUs. We are familiar with them since 70s, but they were developed for the scalar processing and running typical office application or maybe the web application. We have also the GPUs. GPU was designed for the graphics or vector processing, and in some cases they have had some additional cores to help to address some of the workloads specific to machine learning. But essentially, these are processors they were designed for the different purposes. By contrast, the intelligent processor unit, the IPU, has been developed from the ground up, especially for the machine learning intelligent workloads, and to enable more flexible approach to this kind of the models. The IPU, with lots of parallel cores that can do completely separate things to each other, operating on the different data, really enables huge benefits to this new type of machine learning and many others computational workloads. 2 key points need to be taken into consideration when we're discussing effective processor for the machine learning type of the workloads. Parallelism and memory access. On the slide, we see the three different architectures, CPU, GPU, and IPU. And three of those implement the different type of the parallelism architecture. CPU is suitable for the scalar type of the calculation. And this is how the parallelism is executed with the 10 to hundreds of the cores the CPU usually has. GPU, in fact, implements the SIMD or SIMT architecture. If we're discussing this from the Tannenberg taxonomy, we can say that single instruction and multiply data and single instruction and multiply threads, this is the architecture GPU loves. And this is very suitable for the blocks of the very dense configured data. Nevertheless, IPU implements the massive parallelism in completely different fashion using the Nambiar architecture. Multiply instruction, multiply data. And this is exactly what the machine learning workload wants. And this is also very good for the sparsity in the small kernel. On the memory access, we deal with the three different approaches as well. So CPU does memory of the chip. Today is mainly DDR4. The GPU has multi-hierarchy type of the memory architecture with the small memory on chip and bigger out of the chip high bandwidth memory. Today we see the HBM2. Nevertheless, IPU does completely different because the fundamental question is always the same. How effectively and energy efficient you can move the data around your system. And this is basically the limit, how much bandwidth we can effectively deliver with the fixed power envelope. This kind of the trade-off is always the question, how close we can position our memory to our compute elements, and also the question of volume, how much memory we need. But if we really want to maximize our memory bandwidth, we need to distribute our memory through our devices locally to each computer element. And this is exactly what the IPU does. Let's discuss memory trade-off a little bit deeper. If we look at DRAM technology today, we need around 320 picojoule to move byte of data from the memory into the processor core. With the fixed power envelope of 45 watt, we can get up to 140 gigabytes per second memory bandwidth. Looking at the state-of-the-art external memory subsystem, like for example HBM2, embedded with the CPU packaging using the silicon interposer, the energy can drop up to 64 picojoule per byte, meaning we can transfer around the 700 gigabytes per second at that envelope of 45 watts. So we see the significant improvement of the 5 times. Looking at the SRAM at the chip, we see future improvement as well. So we can get up to the 10 picojoule per byte, and improvement is around the 32 times versus the DDR4. Nevertheless, if we really want to maximize our memory bandwidth, we need to distribute our memory to put our devices locally to each compute element. This can drive our energy cost down to the 1 picojoule per byte, deliver at the huge bandwidth of the 45 terabytes per second with the same thermal envelope. And this is what we can do on our IPU Colossus Mark II chip. This is our second generation Colossus Mark II IPU processor, commercially known as the GC200. With the 60 billion transistor built using the latest TSMC 7 nanometers FinFET technology, we built again one of the world's most complex processors. Each GC200 has nearly 1,500 processor cores and runs nearly 9,000 independent parallel programming threads with the proven multi-instruction multiply data processor architecture. Inside the processor, we have been able to put the 900 megabytes of ultra high-speed RAM that runs with the full speed of the machine. Not only we have the 250 teraflops of the AI floating point capability, but we also support much more IEEE float 32-bit compute than any other processor on the planet. Let's have a look on the GC200 IPU processor plan. If we look on the screen, we see the small red square. Those squares represent the IPU tiles. Each tile has coupled the memory subsystem. If we sum all the memories, we will get something like a 900 megabytes of total processor memory. The processor provides 47.5 terabytes memory bandwidth per IPU. The tiles communicate to each other using the IPU exchange. The 8 terabytes per second all-to-all IPU exchange are communicating in non-blocking communication pattern. On the PCI side, we have the PCI Gen 4 64 gigabytes per second bidirectional bandwidth, which is used for communication of the GC200 IPU processor with the host system. IPU has also the IPU links. We have the 10 IPU links with the bandwidth of 320 gigabytes per second, which are providing the communication to the chip-to-chip solution. At GRAPHCORE, we have developed the IPU so that innovators can create the next breakthrough in the machine intelligence. But let me introduce to our platform. All those innovations we have discussed on the IPU level, like massive compute execution, enormous data bandwidth movement, and communication, can be put together in the single breakthrough products called the M2000. The M2000 IPU machine features 4-cylinder IPU engine with the 4 of our new GC200 Mark II Colossus IPU processor, combined with the advanced air-fuel cooling system and fit to easy-to-handle 1U chassis. This IPU engine is combined with IPU fabric, allowing multiply M2000 to be added in the rack, and the racks of the M2000 can be connected together to build large IPU pods. All of this support with the exchange memory subsystem. IPU M2000 machine has the 4 IPUs. It delivers 1 petaflops AI performance. This is our basic building block for the exploration, building and growing the biggest pod. If we take 4 of the IPU M2000, we will get the IPU pod 16. The pod 16 provides 4 petaflops AI performance and is good for the exploration phase. When we will go to the POC level, we will need to have something like IPU pod 64. It is the 16 petaflops AI performance. For the bigger data center integration and innovation in the massive scale going to the exascale computing, we have the bigger pods. IPU pod 128 with the 32 petaflops AI performance, pod 256. The biggest configuration we can build will contain the 64,000 of IPU, able to deliver something like a 16 exaflops of the AI performance. IPU has been built as the machine learning and artificial intelligence type of the workloads processor, but it doesn't mean that the IPU cannot be used in the HPC world, especially that we strongly believe in AI and HPC convergence, and this is what we are going to discuss. But to make this vision successful, we need the new type of the system. This hybridization of the HPC and AI is happening in fact today, as we see that the single monolithic systems are not able to satisfy both worlds, HPC and machine learning. For typical HPC workloads, we have the system based on hundreds, thousands of CPUs and GPUs. In fact, they are also hybrid system in some way. For the AI workloads, as I described on the previous slide, we can use pods, system able to scale to thousands of racks and 64,000 of IPUs. But for new heterogeneous type of the workloads, we required completely new hybrid system, complying the benefits from the both worlds. And this is the way how we accelerate and achieve sustained exascale type of the performance. Our IPU architecture is specially developed for AI type of the workloads and doesn't fit typical HPC application in the pure form. Nevertheless, IPU can improve and extend the HPC classical simulation via surrogate calculation model, which I'm going to explain in a few moments. If we replace the classical simulation solvers using machine learning model, we can achieve great results. This approach uses the data generated during the HPC classical simulation phase to train the machine learning replacement model, which then predict the responses from the new iteration for the experiment much faster. Let's take an example from the CFD. In data generated phase, we use the classical HPC solver to generate the data. Then we use the generated data to build the model and train it. When the new iteration will come, we will use our train already model to predict the results much quicker and much faster. If we look on the diagram in the bottom of the slide, we see that the simulation time can be reduced significantly. Modeling experiment phase will stay in the both scenarios, but simulation time can be accelerated by implemented AI module. Many researchers already use this approach, and in many areas, the integration of AI acceleration model with the classical HPC simulation brings great results. Today, we see spectacular results in the area of high energy physics, computational fluid dynamics simulation, protein folding, Monte Carlo simulation, weather research, or oil and gas exploration. Some of this area I'm going to discuss later because we have the great initial results. This diagram shows our experimental system architecture. Basically, the system contains 4 different types of the nodes and the 5 processes. In the first process, multiply simulation nodes produce the inputs for the multiply machine learning nodes. Then they transfer the data to the machine learning nodes, where weights are used from the previous iteration for the learning. In every iteration, we are updating the weights, making our model more accurate. In the third step, inference can be used for the model which is trained during the ongoing experiment, but we also can use, if we have it, any pre-trained model. Inference output likely needs some processing that can be used in the input for the next iteration. So basically, the processing nodes in the 4th steps transform the data to be useful for the simulation nodes. And simulation restart using insight from the machine learning again. As we can see here, we have the 4 different type of the hardware. Simulation nodes are the nodes from the classical HPC big monolithical system. Machine learning nodes and inference nodes are a GRAPHCORE IPUs machine, and processing nodes are the single x86 machine, which are transforming the data from the inference to the form which are readable for the simulation nodes in the proper format. The first case we have used to examine our experimental system was Deep Drive MD. One of the important problems of the molecular dynamics is protein folding, which aims to answer how to translate proteins from unfolded states into the final structure folded states. If we look on the picture, we see unfolded state protein transformed to the 3-dimensional atomic structure folded states. If we will do this in the classical HPC simulation, you need to understand it is the very expensive simulation time type of the problem. But we found the paper when they are proposing that the surrogate model using machine learning to replace this expensive classical HPC simulation. The reference to the article is mentioned over here, and the title is Deep Learning Driven Adoption Molecular Simulation for the Protein Folding. How we were successful to adopting this model to our surrogates implementation. As I mentioned before, Deep Drive MD takes traditional Markov states model-based solver and replace it by the machine learning-driven approach. We took Deep Drive MD and implement to our experimental system. As we remember, we have the 5 states. In the first simulation nodes, generate the pool of molecular dynamics data of the possible trajectories. Then they send the data to the machine learning pool, which is driven by our pod IPU enabled system. And in the machine learning model, with the network learns how to output the compact representation of the inputs in which similar energetic and structural states are clustered together. Learning is started using the weights from the previous iteration and the initial condition. Then, when the learning is finished, it sends this to the inference node, which is also the IPU enabled. During the inference, neural network reduces the high-dimensional molecular dynamics trajectory to the more compact vector representation. Then, we are just transforming the data to the way that the system can be sent to the simulation nodes. And during the sending the simulation nodes, so in the same time, we are updating the weights for the machine learning model. So in the next iteration, our model has already improved the weights and is the more accurate than it was before. The question is, does this approach improve the performance comparing to the traditional Markov states model based? And short answer is yes. DeepDrive MD runs on the IPU, shows 50% faster training for the batch sizes used in the original experiment versus the leading GPU system. Another experiment we were playing with our experimental system and the surrogate model was the TensorFlow form. In this experiment, the problem given is the computation of the flow path in the back-facing step. In TensorFlow form experiment, we use SmartSim workflow to orchestrate the work between the HPC and machine learning. Together with our partner HPE, we were able to create the system which is containing the classical simulation and machine learning. So we have the four-phase open force simulation when we are running classical HPC simulation. In the second phase, we are getting the data extraction, creating the data sets for our simulation, the machine learning. In the third phase, we are using the training the model, using the TensorFlow and the GRAPHCORE IPU. And in the fourth step, we are improving the simulation inference, modifying OpenFlow solver, utilizing numerical computation in the inference not seen by the classical OpenFlow before. As I said before, is the natural trend to replacing HPC-enabled solver to the machine learning-enabled solver. One of the classic examples is the Juniper notebook produced by European Center of Medium-Range Weather Forecasting. Basically, together with our partner Atos and the group of the engineers for AI4Sim, we took the paper, which is mentioned below, and also implement the Juniper notebook for the IPU, adding additional those lines. This is the only modification we did in the original notebook, and they start training this on the IPU machine. And the results are presented over here. Basically, we are 5 times faster than the leading GPU, but also 50 times faster than the CPU. Another HPC machine learning enabling model we were looking to, it was the CosmoFlow. CosmoFlow replaced trajectories calculated in the Lagrange perturbation theory by a CNN model. The network topology contains 7 3D convolutional layers and 3 fully connected layers, as shown below on the picture. Initial results are very promising. CosmoFlow is running on IPU and achieved the 282 images per second versus 90 images per second on single leading GPU architecture. It was the single IPU to the single A100 machine. We also demonstrate significant improvement in the scalability. So we were able to scale our system almost linearly from the pod 16 to the pod 256. Another model is the Flame21. We're training the convolution neural network to estimate turbulent subgrid scale reaction rate. Surfax proposed new approach for the premixed turbulence combustion modeling based on the UniNet-inspired convolution neural network instead of the HPC classical simulation. We examined Flame21 and we see the significant throughput improvement versus one of the leading graphics subsystem. In terms of the time to train, our IPU-enabled model is also the 8 times more efficient than the GPU subsystem. This ongoing experiment with our partner, KAUST University from the Saudi Arabia, shows the potential of the IPU in the classical HPC workload. In fact, We are experimenting with the general matrix vector multiplication as well with the low-rank matrix vector multiplication provided by counts. The idea is to meet the criteria of 200 microseconds. And as you can see on the slide, IPU delivers the best performance across all the architecture, CPU, GPU, and even vector processor unit, and is the most efficient architecture in the classical general matrix vector multiplication, as also the solver provided by the KAUST University. Thanks very much for the time you dedicate to listen to this presentation, and hopefully I was able to convince you that IPU may play important role in the convergence of the AI and HPC. If you have any additional question, please don't hesitate to contact me. And if you are looking for more information, please visit also our webpage. Thanks very much and goodbye.
Thank you, Professor Pawel Gepner, for this insightful talk. I would just add that it's really nice to have another tool in the quiver when it comes to protein folding on top of AlphaFold and Rosetta 2. The last speaker, before we go on a short break, is Mr. Raghu Nambiar, and the title of his talk is HPC Re-Imagined with AMD EPYC Processors. Mr. Raghu Nambiar, the floor is yours.
Good afternoon, Singapore. Great to be here at the Supercomputing Asia 2022. My name is Raghu Nambiar, responsible for software and solutions at AMD. I was planning to be there in person, but ran into a last-minute logistical issue. So I'm joining live from San Francisco. Thanks for joining us today in the room and virtually. Today, I will talk about the industry landscape at a high level, the key areas that we, AMD, is focusing, our ecosystem partners, and some of the proof points. Please take a couple of seconds to read the cautionary statement. Forward-looking, subject to change, as set out in the cautionary statement here. Okay, let me start with talking about the industry landscape at a very high level. So we are in a very exciting time. I don't know whether I can say we are in a okay. Can you hear me okay? There was a network glitch. So I hope you can hear me okay. So what I wanted to say was we are in a very exciting time in history. We, the industry have been talking about billions of devices getting connected to the internet, for the last few years. No slowdown. We are seeing the emergence of more and more smarter devices getting connected to the internet. And the computing is happening everywhere, at the edge, at the data center, and in the network in between. The data generated by these devices are captured and analyzed using traditional technologies like relational database management systems, big data analytics, and now machine learning and deep learning technologies. 5G is here and transforming how we can connect, collaborate, and do business. Adaptive and intelligent systems are a reality in manufacturing, transportation, and in many other areas. Cloud and multi-cloud is part of enterprise portfolio across the industry. We are in the era of exascale computing and seeing significant investments in the supercomputing space. No doubt that high-performance computing is in the center of our daily lives, touching almost every aspect, whether it is weather prediction or the design of the vehicle, like a bike or car or airplane, traffic patterns, structural safety of your building, the vaccination to protecting all of us. All these need a lot of compute power. But if you look at today's data centers, they're under tremendous pressure to deliver more for less, more performance, more scalability at a lower budget, while meeting security and compliance requirements. Whether it is general purpose computing, simulations, or design automation, our customers demand efficiency and lower cost of ownership. This requires new thinking and innovation. AMD has a long history of innovation. Over 50 years, we have been innovating. Today, we have a very strong portfolio of CPUs, GPUs, and FPGAs too. That said, my primary focus for today's presentation is going to be the CPUs. AMD made a big comeback in the data center space with the announcement of EPYC processors in 2016, with a set of industry-leading innovations in core density, memory bandwidth, memory capacity, and high-speed I/O. Today, the third generation of EPYC processors offer industry's highest x86 core density, 64 cores per CPU. That means in a two-socket system, you can pack up to 128 cores and 256 threads. We are the first to bring DDR4 at the 3200 MHz to the market with our third generation EPYC processors. Supports up to 8 memory channels, supporting up to 4 TB of memory capacity per CPU, and in a two-socket system, you're talking about 8 TB of memory. First to deliver PCIe Gen 4 up to the x86 world, enabling high-speed I/O, network connectivity, and also accelerated connectivity. AMD EPYC processors also include innovative hardware-accelerated encryption technology called SEV, Secure Encrypted Virtualization, which enables confidential computing. The confidential computing is a relatively new term. Designed to cryptographically isolate virtual machines from each other and from the hypervisor in a cloud environment. This is very innovative solution. Today, Azure and GCP offer confidential computing based on AMD's SEV technology. VMware and Nutanix are offering confidential computing with our SEV technology in private cloud environments with the HCI offers. An important point to note is that SEV is completely transparent to your application. No code changes or recompilation required. Things work out of the box. That said, I wanted to flash the list of SKUs in the third generation EPYC family, 8, 16, 24, 32, 48, and 64 cores. I know the font is a little small, especially for online audience, but the slides will be available to you. The key point I want to make is that there is a wide range of configurations to address nearly every workload and budget. Whether you're running HPC, related database management systems, big data analytics, or building a software-defined infrastructure, private cloud or public cloud, AMD EPYC offers the performance and efficiency. Available both in single socket and dual socket configurations. Single socket is great for many applications and offer much lower total cost of ownership. But if you need the full performance, full memory bandwidth and capacity, then of course the two socket systems are the way to go. Okay, I said that AMD EPYC processors were introduced in 2016. Let's look at the momentum. We are seeing tremendous momentum across clouds, enterprises, and in the HPC space. Today, AMD EPYC processors are powering over 400 public cloud instances. There are over 100 server platforms based on AMD EPYC processors. HPC is one of the key area of focus, of course, but we are seeing great traction for enterprise workloads as well, like database, analytics, and other applications. It is exciting to say that 8 of the 10 most efficient supercomputers are now powered by AMD CPUs and GPUs. Now let's talk about world records. Okay, we have a history of demonstrating leadership through industry standard benchmarks in performance, price performance, and energy efficiency. We are proud to be able to showcase over 250 world records as of date for a wide range of applications. This includes data management, business applications, software-defined infrastructure solutions, and HPC and technical computing. These proof points are direct result of our silicon innovation and strong engineering collaboration with our ecosystem partners. So we are really proud to have a very strong ecosystem of partners. We jointly bring innovative platforms and solutions to the market. I want to thank HP, Dell, Supermicro, Lenovo, Atos, Gigabyte, and others who has created highly optimized platforms and solutions for your HPC deployments. So I also want to acknowledge our ISV ecosystem partners, ANSYS, Altair, Siemens, Cadence, Synopsys, Emerson, Dassault Systems, Shearwater, and others with whom we closely collaborate on software optimizations. We are making significant investments in platform and software engineering. So we have regional customer POC labs if you're looking for a POC, and have a strong team of HPC solution architects as part of our global sales organization. I'm pretty sure few people are in the audience today in Singapore. So please talk to them again if you're looking for additional information or an opportunity to do a proof of concept. Okay, hyperscalers are a major part of our portfolio. Today, 10 of the world's largest hyperscaler companies are designing EPYC into their data centers. AWS, Alibaba, Baidu, Google, IBM, Meta, Oracle, Microsoft Azure, Tencent, and Twitter. As I said before, there are over 400 cloud instances powered by AMD EPYC processors, powering various digital services, software as a service, platform as a service, and of course, infrastructure as a service solutions. Now let's look at the HPC on clouds. Let me start with Azure. HB-V3 instance is optimized for HPC applications such as computational fluid dynamics, finite element analysis, weather modeling, RTL simulation, and more. HB-V3 features AMD's 64-core CPUs. Network performance plays a key role in scale-out computing. HB-V3 is unique in that aspect, featuring 200 gig HDR InfiniBand interconnect in a non-blocking FAT-free network topology. We have demonstrated up to 89% performance uplift generationally and super linear scalability for many applications on Azure HB-V3. So Google is another strong partner of AMD. Google C2D is a compute optimized instance that comes in 3 flavors: standard, high CPU, and high memory, giving you the option to pick the optimal configuration based on your workload demands. Up to 66% performance uplift over N2D instance powered by previous generation of CPUs. AWS HPC 6A is a compute optimized instances that are designed for a variety of applications, batch processing, media transcoding, machine learning workloads, and HPC. We have demonstrated near linear scalability for several workloads, including STAR CCM, a popular CFD application, and WRF, a popular weather modeling application, as you see on the screen. We are making significant investments in software optimizations and solutions with our ecosystem partners in important areas such as finite element analysis, structural safety and designs, weather forecasting, computational fluid dynamics, oil and gas applications, and more. The EDA is another key, a very important area that is not listed here. We understand that time to value has become a key KPI in HPC. We work very closely with our ecosystem partners in optimizations that results in leadership performance in several areas. Let me call out a few. Let me start with ANSYS LS-DYNA. LS-DYNA is a multiphysics simulation software capable of simulating complex real-world problems. It is used in automobile, aerospace, construction, manufacturing, and in other areas. This workload is highly frequency sensitive and memory bandwidth intensive. At 32 core, our 75F3 processor delivers 33% better performance than Intel's Ice Lake 8362. Okay, please note that this comparison is not based on our top of the SKU, but based on middle of the stack 32 core CPUs, keeping the core counts the same for a fair comparison. Another workload that is WRF, accurately predicting weather is critical for our daily lives and in businesses such as transportation, agriculture, and energy. WRF is a very popular model in weather forecasting. 13% performance uplift, as you see on the screen, means 13% less servers. These cluster deployments are typically in hundreds and even thousands of servers. So the savings can be significantly huge. Another application I want to call out is computational fluid dynamics. Is applicable in a wide range of problems in research and engineering, aerodynamics, life sciences, industrial designs, environmental engineering, and to name a few. CFX is a very popular CFD program from our partner ANSYS. At 32 core, EPYC is 43% better than Ice Lake. That means 43% more simulations, leading to a faster outcome and better design accuracy. Oil and gas is one of the largest industry verticals. Seismic surveys have been used for offshore and onshore mineral and oil exploration for last 5 decades. Shearwater's Ravel is a modern seismic processing software. Our internal performance benchmarks show that a 37% performance uplift versus a 32 core Ice Lake system. I gave a few examples here. The examples here on performance advantage of AMD's EPYC processors. The key point I want to make is that the performance advantage of EPYC processors can help you with faster simulations, lower time to value, and of course, lower cost of ownership. Now let's look at the computational science in the context of supercomputing. Computational science is more critical than ever in helping the humanity to address some of the most important challenges: the climate change, the ongoing fight against COVID, search for search for cure for deadly diseases such as cancer, journey towards carbon neutrality and sustainability. These are very complex problems and very important, impacting the humanity. So supercomputers have been playing a key role in computational science, addressing some of these problems for years. So AMD has a long history in the supercomputing market segment. Since 2005, AMD has powered some of the largest supercomputers, now powering 73 of the world's top supercomputers. The number was 21 in 2020 and 11 in 2019. Since the introduction of AMD EPYC, the adoption of our CPU and GPU technologies in the supercomputers has significantly gone up. Now, we are leading the exascale compute era in partnership with our server OEM partners like HPE, and Cray division of HPE. Let me give you like two of the marquee examples here. The Frontier supercomputer at Oak Ridge National Laboratory is expected to have a compute power of 1.5 exaflops. The El Capitan supercomputer at the Lawrence Livermore National Laboratory is expected to have a compute power of 2 exaflops. Both these exascale systems are powered by AMD EPYC CPUs and GPUs, as I said, built by HPE, a very strong partner of AMD. Some of the other major supercomputing wins are listed here. Okay, so we have a very strong roadmap. The first generation of EPYC, codenamed Naples, was introduced in 2016, as I said in the previous slide, which was based on 14 nanometer technology. The second generation codenamed Rome was introduced in 2018, based on 7 nanometer technology, with the doubling the core density, high-speed DDR4 memory, PCIe Gen 4 for high-speed I/O connectivity. Current generation, the third generation codenamed Milan was introduced last year, with a significant improvements in per core performance and the socket level performance. As I said, we have demonstrated the capabilities through 200 plus world records in important areas. We continue to innovate chip design and manufacturing. The fourth generation of AMD EPYC processors will be manufactured using 5 nanometer technology, with yet another set of innovations on core performance, density, memory, and I/O bandwidth. With even greater performance and efficiency, we will announce our next generation processors. That said, thank you very much for your time. I can take a couple of questions if there are questions in the room.
Thank you, Mr. Raghu Nambiar, for this interesting talk. I also would like to thank everyone that present here and those that tuned in virtually. We will now have a short break until 3:50 p.m. when we will reconvene for the next tour that will be ever so slightly different than the sessions that we had now. And I really hope to see you all here. Thank you.